Okay, everyone, welcome back. How are y'all doing? Any questions? Yes? Questions? No? Bonus? Oh yeah. That odd, that even problem. Anyone else? No one else? No? All right. Which one? 54? Yeah, all those constants and stuff, right? Yeah. Okay. I want to start today's class with an integral that came up. I did a makeup test for some students who weren't here for the test, and at some point they got to this integral, and it seemed to cause some issues. So we're going to actually talk about something like this today, right? Like how to go about this problem. So it's kind of naturally suited for our discussion. Um, First thing maybe you might be looking at when you look at this integral is a basic substitution. Do you see something in its derivative, right? Maybe. Let's try something here. Let's try u equals x squared plus 1 and du equals 2x dx. I don't have a 2x dx, do I? I do have an x squared up top, so I could, if I wanted to, rewrite this integral x over x squared plus 1 x dx, right? And then I almost have 2x dx, right? I'm just off by a constant. And so maybe this will somehow work. I'll scale over here. 1/2 du is x dx. And now let me rewrite the integral. So this integral becomes integral. Let me take care of the bottom. The bottom is u, right? This over here is 1/2 du. But what's x? Oh, wait, hold on. Yeah, this is right. What about that x, though? I would have to take this equation here, right, and solve it for x. So move the 1 over, and then take the square root, right? So now I have square root u minus 1 over u, right? And I can pull the 1/2 out. Let me bring this over here. 1/2 integral square root u minus 1 over u du. But that doesn't seem to really make it much better. I mean, it helped a little bit, but I can't split that into two fractions, right? Because the u minus 1 is trapped under the root. So what, right? See what I'm saying? Kind of stuck? Yeah? Okay, so let's, instead of doing this, let's talk about what we did last class, the last problem I gave you in class. We took something like this, and we applied long division to it, right? We did long division inside. So what is x squared divided by x squared plus 1? So you have to ask yourself, what do I multiply x squared by to get x squared? 1, right? Okay, then you multiply that 1 times both of these terms and then put those underneath, right? So what would we get there? X squared plus 1 here. But then you have to come through and subtract this, don't you? So subtract, subtract. So what are you left with there? Just a negative 1, right? And that's your remainder. So what I can do is I can say up here where my division box is, I can say plus my remainder negative 1 over the divisor, which is x squared plus 1, right? That means this integral becomes 1 plus negative 1 over x squared plus 1 dx. And can you integrate each of those term by term? Do you know what the antiderivative of 1 is? Yes, right, just x. And then this 1 over x squared plus 1 actually looks like arctan, right? That's the derivative of arctan. So that's one of the formulas that we should start to recognize when we see it, right? Derivative of arctan x is 1 over 1 plus x squared, or 1 over x squared plus 1. You'll follow this? Yes? So we get from here equals x, I'm going to say minus arctan x plus a constant, and then I'm done. Make sense? Is there another way I could have approached it? Sure. How about this way? Last class we learned about trigonometric substitutions, didn't we? And we said, what do we do when we see a square root of a squared plus x squared? We made a substitution, x is equal to a, which one is it? Tangent theta, right? That was our substitution. So for this problem, first I need to see a square root, right? I don't know why my computer keeps doing that. It's weird. Okay. I need to see a square root. So here it comes. I can rewrite the denominator as the square root of x squared plus 1 squared dx, can't I? And then our substitution here is x is equal to just tan theta because a is 1, isn't it? And that means dx is secant squared theta, d theta. And the square root of 1 plus x squared, if you go and work that out, you should just get secant theta. Now how can I rewrite the integral now? What's x squared up here? That's tangent squared theta. Okay, so tangent squared theta. Any questions? Man. What's the square root thing turn into? Secant theta, but it's squared, right? Because I've got that squared right there. Right, so I've got to square that. So I should have secant squared on the bottom, theta. And then dx turns into what? Secant squared theta d theta. And then the secant squareds cancel. That's nice. Right? And so I get tangent squared theta. D theta. How would you do that? Good. Turn that into 1 minus secant squared theta d theta. And that you can do the antiderivative of each one, right? What's the antiderivative of 1? Be careful. Careful. Theta, right? Theta. And then the antiderivative of secant squared is tangent theta plus a constant, right? You with me still? But now I need to get everything back in terms of x. So remembering that earlier I made the substitution that x was equal to, what was it, tangent theta? right? Then I need to know what theta is, right? So how can I get theta out of this equation? Take arctan on both sides. Arctan x equals theta. And so my theta becomes arctangent x, and my tangent theta becomes, what's tangent theta? X plus c, right? Agreed? Hold on a second. I realize what happened. This is wrong. This should be 1 here and plus. Change that. Look at the identity is this 1. Yeah, it's secant squared minus 1. 1 plus tangent squared theta equals secant squared theta. My bad. Sorry about that. Y'all see what I'm saying? When I was trying to replace tangent squared theta right there, I'm using that identity. Should have moved the 1 over, which would have made it -1 and positive secant squared. That's just going to change the signs, right? It's going to make this minus, this plus, this plus, this minus. And doesn't this answer match the one we did before? Right there? Matches this. X minus arctangent x, right? So I've shown you what? 2 different approaches to this, right? Which one do you think is cleaner? That one? The long division, right? That was super clean, right? Because as soon as I did the long division, I could go straight to integration, right? I didn't have to do a substitution. This one, although it worked, required more work, right? And I'm going to show you a third way, all right? This way is super sneaky, all right? But it's one of those tools that you should know is available to you. I mean, this is really, really clever, what I'm about to do here. Okay, in most math classes that you've been in, you've always run into this thing where you're like, oh, you know, you can always take anything and multiply it by 1, right? And you would write that 1 as maybe like a 4 over 4. Or you would write that 1 as something over something, right? I mean, how many different times in our math lives have we like multiplied something by 1 and made that 1 look like something we wanted it to be, right? Well, that's somewhat of a high level of thinking. But in higher level of thinking, you can look at everything as having a 0 next to it being added. So look at this x squared on top. Everyone agree that's the same as x squared plus 0, right? So I'm actually seeing a hidden 0 next to it, right? Now watch this. X squared plus 1 minus 1. Isn't x squared plus 1 minus 1 the same as x squared plus nothing? Right? Maybe if I do it this way. I mean, I'm sure you see it, but I've got these colors, I may as well do it. That's still 0, right? That plus 1 minus 1. But by doing it that way, I can now break up my numerator right down here, right? Just split it right down here and do the first 2 terms over the denominator, second term over denominator. You see that? And watch what happens. You get the x squared plus 1 over the x squared plus 1. And then you get, what, minus 1 over x squared plus 1? Don't you? And what is this first fraction right here? What's this? That's 1, isn't it? Can you take the antiderivative of 1? Sure, that's going to be x. And then the other one, minus, what's the antiderivative of 1 over x squared plus 1? Arctangent. Sneaky, huh? Hidden zeros are, like I said, a higher level of a math skill to see hidden zeros everywhere. Mm-hmm. Yep. Okay. All right, we're going to move on now partial fractions. We started this last time, but now it's time to kind of get into this. Whoa. Why is it so large? Oops. All right, well, this is not all fitting on the screen. Let me see if there's any way I can zoom this out. Zoom out. Awesome. Okay. All right, partial fractions. We actually have a procedure, finally, right? Instead of just looking and like trying to figure things out, we actually have a procedure for doing integrals that look like this. So, of course, you'll be able to access all these notes. I don't know, I sent out an announcement. Everything I write down, you know I'm doing video of, but I'm also sending them out as PDFs. So you can, you don't need to invest too much energy copying down things like this because you can get to it later, okay? So, partial fractions. When we have, anytime we have an integral where we have a polynomial divided by a polynomial, what we want to do is follow this procedure. And here's the first thing. If the degree of the numerator is greater than or equal to the degree of the denominator, then we have to do long division first. Okay, so like in the problem we just had, this problem right here, right? We have a polynomial divided by a polynomial. And so I check to see what the degree of the numerator is. What's the degree of the numerator? 2. Is that bigger than or equal to 2? Bigger than or equal? Yes, it's equal, right? So the first thing I would do is long division, right? Now, if you knew that super tricky trick, right, then you could do that also, but we can see that this would be kind of our procedure. This way, the long division would be the way we do it if we didn't see that trick, okay? So going back here, we'll do long division first, and that will give us, a new integral that'll have some terms in it. What you'll do now is you'll look at what's still there, and you'll factor any denominators that you have that are still like polynomials, because remember your remainder will always be the remainder over the divisor. That divisor is the polynomial in the denominator, the original one. So you want to try and factor it. So factor the denominator. And then what we'll have, at least in this class, all right, we will look at 4 possibilities of what that denominator has in it. Your denominator, when you factor it, could have a linear factor that's an ax plus b. If your denominator has an ax plus b in the denominator, right, one factor, then for each of those linear factors that you have to create an a over ax plus b. So this is like what we did last class where we were taking something and we were factoring it out or doing the partial fraction decomposition of it. Y'all know what I'm talking about or not? Yes? We're going to do examples, so you'll see how this is all going to work. So for each one of these we see, we have to create one of these. Now, if you have a repeated linear factor, that means you have a factor in the denominator that's raised to a power like 2 or 3 or 4, then what we have to do is this. So this means a number a1 over the linear factor, then another number a2 over that linear factor squared, then another number a3 over that linear factor cubed, and we keep doing that until we get to the last power. So if this was a 5, we would have this over this squared, this over this cubed, this over this to the 4th, this over this to the 5th, and that's when you would stop. Make sense? We'll see it play out here. Then you look at you might have a quadratic factor. That means your denominator might have something that's quadratic, and we know that not all quadratics factor. So if you can't factor it any further, then you would have to have this. You would make that appear in your partial fraction decomposition. Let's look at what it is. It's a number in front of x plus b. So you have a linear expression up here over your quadratic. See, ax plus b is linear, right? Over that quadratic. If you have a repeated quadratic factor, so that you have a power on it, then you have to do linear over it, linear over that squared, linear over that cubed. Keep going until you get the highest power k. That's the way we do partial fractions. Now, me saying it is one thing, me actually demonstrating is something else. And then this last thing, don't worry about this one right now. this is what I gave you last class. Remember that? If you have 1 divided by a linear factor and you want to integrate it, then it's 1 over a natural log of that. Okay, so I'll refer back to this if need be. Let's get to a new page. Let me get my zoom back to 100%. All right. Examples. Okay, let's do integral y over, let's go x. I'll keep it with x. X over x plus 4, 2x minus 1 dx. So the first question is, do you see a polynomial divided by a polynomial? That's right. That reminds me, I don't think mine's turned off. I'm sorry? Well, is x a polynomial? Is x a polynomial? Polynomials are expressions that have powers, integer powers of x. So like x to the first power, x squared, x cubed. So that is a polynomial. It's a line, it's linear, but all lines are polynomials. So that in even constants, 4, the number 4, the number 5, those are polynomials also. Okay? By themselves, yes. So like if you had like x squared plus 2, that would be a second degree polynomial. If you have x to the 5th minus 7, whatever, that would be 5th degree. If you have x, that's first degree, and if you have the number 4, it's a 0 degree. Because it's like if you write 4, that's the same as 4 times x to the 0. Right? Okay. So that is a polynomial divided by a polynomial, right? All right. Next thing. Make sure that you look at the degree. So what's the degree of the numerator? I'm just going to put here degree numerator is 1. What's the degree of the denominator? If you multiply those out, you would get x squared, wouldn't you? So this is degree 2. So is the degree of the numerator bigger than or equal to denominator? No. So I don't have to do long division, thank goodness. So now I can go straight to the next thing, which would be to factor the denominator. It's factored, right? So I don't have to do that step. So now what I need to do, and this is going to be like scratch work, I'm going to come back to this integral in a second. What I'm going to do is I'm going to rewrite the integrand. Is it? It's probably because of where I'm sitting. And what I need to do is for every linear factor, so isn't x plus 4 a linear factor? Right? For every linear factor I see, I do a number, a, over that linear factor. Right? So I'm going to do a over that linear factor, x plus 4. Am I still lagging or no? No. Let me know if it happens again. Now I have another linear factor, don't I? 2x minus 1. So I need to do a number over that linear factor. And I add it over here. So it's plus. Now I can't use a because I already used a, right? So I'm going to use capital B. And then 2x minus 1. And do you remember what we did at this juncture? What did we do? We multiplied both sides by the LCD, which is the denominator on the left-hand side. So I'm going to come in here now and I'm going to multiply the left side by x plus 4 times 2x minus 1. And I'm going to do the same thing over here, x plus 4 times 2x minus 1. And I got to be careful here that I distribute that through. On the left side, you should always get the same thing happen. You should just get your numerator, right? Denominator is going to cancel. On the right side, when I do my first multiplication of this one through to this one, the x plus 4's cancel, right? So I'm left with a times 2x minus 1. When I do my next multiplication of my LCD through, my 2x minus 1's cancel, and I'm left with b times x plus 4. Y'all with me? Anyone have a question? Do y'all remember what I did last time at this point? Yeah, this is where I was talking to y'all about the little God complex, right? You come in, you get an opportunity to pick x, choose it to be whatever you want, so that it kills off one of the terms on the right side. So let's kill off b first. Okay, so I'm going to try now to kill b. To kill b, I'm going to let x be what? Negative 4. Now rewrite this line right here, replacing the entire, every x you see with negative 4. So negative 4 equals a times what? What's that going to be? Negative 9, right? And then plus b times, that's going to be 0, which is the reason I did it. So we get a is what? 4 over 9. So I know what a is. And then, any questions on that? How about b? So what should I let x be? Let x be 1/2 should work, right? All I'm doing there is I'm asking myself, what makes that 0, right? What makes that 0 so I can kill it? Solve that for x. You get 1/2, don't you? Unless you just look and you see it. You can do it that way too. All right, so let me let x be 1/2. I'm going to rewrite that entire line with x being 1/2. Crap, I'm going to have fractions. 1/2 equals a times what's going to happen here? It's going to be 0, right? Plus b times 1/2 plus 4. So 1/2 equals b times 9/2. 4 is the same as 8 over 2. And then you add 1/2, you get 9 over 2. How would you get b? How would you get b here? I would do the multiplication of the reciprocal on both sides. I would just multiply both sides by 2/9. Because the 2's will go, the 9's will go, and then on the other side you get what? 2/18, which is 1/9, is b. What's that? Yeah, now what we do is we come back up here, right? This was the work that we had done. Our whole goal was to try and figure out what a and b were, right? I'm just going to go and rewrite those with my a and my b, but I'm also going to throw them into the integral. Because all I've done is I've transformed this integrand, which is this, into this, and I actually know what the a and the b are, right? So here's my new integral. I'm ready to go to town on this. It's going to be integral, and I'm going to have two terms. It was a, which was 4/9 over, make sure you get the correct linear factor here. Which one was the first one? Was it x plus 4? Go back up here, look at it. Yeah, the a is over x plus 4, right? A is over the x plus 4. So I'm going to come back down here, a over, let's see, x plus 4. And then we have plus b, which was 1/9 over the 2x minus 1, and then dx. That okay? Now, I'm just going to go one more step since this is one of the first examples I'm showing you. I'm going to pull the 4/9 out of the integral and be left with 1 over x plus 4 dx. So that's one integral. And then the other one I'm going to split up here, pull the 1/9 out, integral 1 over 2x minus 1 dx. So does everyone see all I've done is just split that into two integrals? Pull the constants out. Now each of these integrals are in the form 1 over ax plus b. And the antiderivative of 1 over ax plus b is 1 over a natural log of ax plus b from last class, right? So what do I get now? I'm integrating. I've got my answer here. It's 4/9. Then what? ln x plus 4. And we're technically supposed to have an absolute value around there. Plus 1/9, be careful, times 1/2 natural log 2x minus 1 plus c. And of course, 1/9 times 1/2 is 1/18, isn't it? All right, that's it. What do y'all think? Is that okay? Yes. The formula for doing this right here, okay? That doesn't help. All right, the formula for doing that one right there from last class. Come on, man. That formula right there, that top one, right? This right here is this, okay? James, I'm going to point out what you showed me. So someone brought this to my attention that on the video from last time, or on the notes, where the hell are the notes from last time? Where the heck is it? Okay, from last time. What happens is when I start a new page, this Microsoft OneNote automatically tries to name the page. So like for the page over here, right? See, this is the name of the page. It's trying to interpret this handwriting into words. So it thinks it's cost tax ax, okay? And then in the next page, it's interpreting that first thing there as an is. I don't know why. But look at the next one. Thinks sex did. And so I think it appears up here, right? It appears up there. So James thought that I had left one of my windows open on one of my web searches or something like that, when it actually wasn't. It's just the program. Too bad. I always close my web pages. Okay. So I don't think that there's not like a super shortcut for this problem. That's pretty much it. Okay. I mean, maybe there's some manipulation we could do. Let's go to a different problem. Was that fun or what?
So if you had, say, like, the integral of x over x plus 4, and that's it, you can just do x plus 4 minus 4 and split it up.
Yes. Uh-huh. Yep. That would be a clever way of approaching it. Absolutely. Okay, how about this one? Integral x cubed minus 4x minus 10 over x squared minus x minus 6 dx. See, I don't know why it does that. Dx. So you look at it, first thing, polynomial over polynomial, right? Degree of the numerator is what? 3. Degree of denominator is 2. That means long division first. All right, long division. Here we go. Now be careful on your long division because we have an x cubed, right? But we don't have an x squared, so I'm going to leave a space and then minus 10, right? So I've left this space intentionally. In case I get x squareds, I'll have a place to line them up when I do my division. And then on the outside of the division box, x squared minus x minus 6. Go ahead, you try it. See if you can get that division on your own. Did I tell y'all I learned how to sew this weekend? Did I share that with y'all? No? Check this out.
That's still a little sketchy, don't you think?
I'm not going to turn it all the way over, but I won't drop it. That's for sure. It's not going to slide out of my hand. So I sewed Velcro onto my glove. It was kind of fun. What's that?
You can buy that stuff with sticky on the side, so you don't have to.
On the glove? The glove has it on it?
Yeah, they have Velcro tape that you can just attach.
I don't trust the tape though.
It's pretty good.
Is it good? See, because I'm using that on this. I put it all it's all on the bottom of the laptop. I tried to make sure I didn't cover any of my vent ports and stuff. All right, come on, y'all go. Sewing's interesting, man. That's a skill. I didn't. I did good, man. I did good. I had a couple of test things first. All right, I'm just gonna put the work in here, okay? While you're trying to do it on your own, I'm gonna put it in here. When do you stop doing division? When do you stop? Anyone know? You stop when the power of what you have down here is smaller than the power of what you're trying to divide by. See if you can get up to that point. For those of you who are trying to work it, see if you can get to at least that. But that should be, hold on. I forgot to bring my 10 down. What the heck? I forgot my 10. How many of you are okay with that up to that point? Yes? So this is where I stop long division. I stop long division because the power of what's down here is smaller than the power here, right? I have x squared there. So that's where I stop. So that's my remainder. My remainder is not a number now. It's actually a linear expression. So what I would do is I would write plus, I'm going to have to go sideways here, 3x minus 4 over my divisor, x squared minus x minus 6. Follow that? Sorry, it's off the board. Okay, so I'd like to proceed. Can I proceed? All right. All right, so my new integral is integral of x plus 1 plus 3x minus 4 over x squared minus x minus 6 dx. Is that all right? Can you integrate those first two terms? Antiderivative of x, 1/2 x squared. Antiderivative of 1 is x. So those first two are fine, right? Now we need to focus our attention on this one right here. And so we're back to where we were before. We have a polynomial over polynomial, but now the power of the top is smaller than the power of the bottom. So now we go to the next thing, which was to try and factor the bottom. Can you factor the bottom?
Yes.
Absolutely. So what I'd like to do at this point is I'd like to put like a squiggly line saying I'm just going to focus my attention on this integral. And I just need to remember to come back and fill everything in at the end. Oh, let me factor it. It factors to be what? X minus 3, x plus 2, right? Dx. And I have how many? Well, someone tell me about my denominator. I have what?
Two terms.
Two,
Two sets.
two, two, what are these called?
AB.
X's factors.
They're factors, and they are both linear. Okay, we have two linear factors, right? That's what we have, two linear factors. So for each linear factor, I need a number over the factor. So I'm going to do my partial fraction decomposition now. So this is where I do need to come in here and say, hey, look, I'm going to come back to the integral. Let me rewrite 3x minus 4 over the x minus 3, the x plus 2. That's going to be equal to some number a over x minus 3, and then plus some number b over x plus 2, right? Okay. Now, I'm not going to go through the whole thing. LCD on both sides, right? If you do LCD on both sides, you get 3x minus 4 here. Over here, you get a, x plus 2, and then over here, plus b, x minus 3. And now we go try and kill things off, right? So let's kill them off. Let x be what? I'm gonna kill the b first. We'll come back and be careful. I want to kill the b, right? If I want to kill the b, I need to make the x minus 3 turn into a 0. So I'm going to let x be 3. If you do that, what do you get? So you have to replace everything in this line, all your x's with 3's. So 3 times 3, right? 9, take away 4 is 5. And then you'll have equals a times 5, right? 3 plus 2 is 5. So that's 3 plus 2 is 5. And so divide by 5, a is 1. Good for us. Any questions? All right, now let x be what? Negative 2. Now I'm trying to kill off the a. If I do that, I get, what, negative 10? Because I plug a negative 2 in right here. 3 times negative 2 is negative 6. Take away 4, negative 10. The a is going to go away. And then over here, I'll have negative 2 take away 3 is negative 5, right? So the other side is b times negative 5. Divide both sides by negative 5. B is 2. So if I want to, since it's right here, I'm going to replace that a up there with what, 1? I'm going to replace that b up here with a 2. All right, we're there. We have to just do the integration. So I'm back now to the original problem. The original integral turns into, what was it? X plus 1 plus what we just figured out, which was 1 over
x minus 3
x minus 3 plus 2 over
x plus 2.
x plus 2 dx. Everyone okay with that? The x plus 1 came from our long division, and then this is how we decomposed that polynomial using partial fraction stuff. And that integration should be straightforward. 1/2 x squared plus x plus natural log x minus 3 plus 2 natural log x plus 2 plus c. That's it. What's that? Where the what? That 2 right here? That 2 just came from here. I just pulled that 2 out in front. And then it was 1 over that. And so I'm not going to go through this problem completely, this next one. I'm just going to set it up and see how you would do on your own with it. What about something like this? Integral x squared plus 2x minus 1 over x cubed minus x dx. It's already 150. Damn. Polynomial over polynomial. Do we need to do long division? No? No long division, right? Okay, so try and factor the denominator. So I'll do that over here. X cubed minus x. If I try and factor that, that's x. I'm pulling out a GCF. Times x squared minus 1. And that's x times x plus 1 times x minus 1. Right? So I just pulled out an x, then I did difference of squares. So let me do my partial fraction stuff here. X squared plus 2x minus 1 over the x times x plus 1 times the x minus 1 should turn into, so what am I looking at in the denominator here? What do I have? 3 linear factors, right? So for each linear factor, I need a number over it, right? So it's going to be a over x, because x is a linear factor, right? X is just x. It's like 1x. Okay, plus what? B over x plus 1, and then plus a third one, c over x minus 1. Let's hope that we don't have 25 linear factors, right? Because we'll run out of letters, won't we? We're already using x. We could use A, B, C, D, E, F. You're never going to have that many, but if you look at a book, and if you look at even my notes, what I did earlier, look, where is that thing? Do you see how in this note up here I put like A1, A2, A3? We subscript like that in math because you never run out of letters that way, right? I could have done A, B, C, D, but if you have more than 26 of anything, how are you going to represent it with letters, right? So subscripting like that allows you to go as far as you ever need to go. Just FYI. Okay, so back to this guy. So what would you get? You have to kind of be careful here when you multiply through by the LCD. Left side, you know, it's just going to be that numerator. Yeah, it's basically going to be canceling out all the ones on the bottom. So you'll have the A, and then you'll have x plus 1, and you'll also have the x minus 1, won't you?
Can you just put it together?
I don't recommend putting it together. You'll see why. You get the B, and then what? What's here? X and x minus 1. and then plus c and what are you going to have? X and x plus 1? You'll see that? Now, same game. We've got to kill things off. So I think I might wind up working through most of this problem now that I think about it. Is there a way that we can determine what A is? If we're going to try and figure out what A is, we've got to kill off B and C at the same time. X is 0. See, the B and the C are the only ones that have the X by itself, right? So if I let X be 0, I'll kill those two, but I won't kill these. See what I'm saying? So I'm going to try and find A by letting X be 0. If I do that, let's rewrite the entire line there. What would you get? -1 equals A times 0 plus 1 is 1. 0 minus 1 is -1, so it'll turn into -1. Yes. So A is what? 1. Nice. Questions? Okay, how are we going to get B? So I want to preserve B. I don't want to let X be what? 0 or 1, right? So can I kill these two guys off without killing this one off? Yeah, let X be -1. It'll make this a 0. It'll make this one a 0. But it won't make these zeros, right? So let X be -1. Plug in. That left side's going to take a little more work. -1 squared plus 2 times -1 minus 1. -2. Equals, A's gone, isn't it? C's gone. The only thing there is B. And I plugged in -1, so -1 and then -1 minus 1. So 2. Still no questions? Questions? No? Yes? These two multiply to become -1, and then you divide by -1.
No, I get that one. The next line. Wouldn't you still have, when you plug in -1 to the, where the x's are, next to the A?
-1 right here would go to 0. Right here, this will go to 0, but this one wouldn't. This one would be -1, and that would be -1 minus 1. Got it? Okay. So this right here is -2, right? This guy right here is -2. And then that's -1, so -2 times -1 is 2. And then divide by 2 on both sides, you get B is what? -1. And finally, to try and get C, I'm going to let X be what? 1. Nobody has a question as to why I'm choosing my X's that way? Because that's the most critical part of everything. Okay, you're just doing it? All right, let's plug 1 in. What do you get, 2? Equals, everything's gone except the C times 1 times 1 plus 1, so 2. So C is 1 also. Beautiful. So I know my A is 1, my B is -1, my C is 1. And I'm ready to write down the integral. The integral becomes, and I never did synthetic division. I never did long division, so I just write these 3 terms out. 1 over x plus -1 over x plus 1 plus 1 over x minus 1 dx. Bless you. So what's my answer here? ln x minus ln x plus 1 plus ln x minus 1 plus c. There it is. Are you catching on to this? Yeah? You sure everyone's comfortable? Because It's about to get harder. Okay. I need to stand up, stretch out for a second. Up to this point, when we're trying to find our A, B, and C, we've been able to pick a clever X to make things go away so we could isolate the A, B, or C and solve for it. It's been pretty clean, right? This next example, you'll see we're not going to be able to do that. And so we need to have another way. All right, so we're going to call this the shortcut way, where we're letting X be something to get A, B, and C. That's kind of a shortcut. But if that fails, this next example demonstrates how you do it. Here we go, rock and roll. Integral x squared minus 5x plus 16 over 2x plus 1 times x minus 2 squared dx. So we have, first time this has happened, we have a squared here, don't we? Do we need to do long division? Why not? The power of the numerator is 2, right? The degree. Now the denominator it's not multiplied out yet, but if you did, you would get a cubic, wouldn't you? Because you would take this first and you would square it, which would give you a quadratic. Then you would hit it with that 2x and it would become cubic. So the bottom has a degree of 3, top is 2, so no long division required, right? All right. Now factor the denominator. Yay, it's factored. Okay, we don't have to do that. It's already broken down, isn't it? As you might imagine, you're going to get problems that aren't factored. So you'll have to get them to this point and then do the work. But we're just, baby steps, right? Let's talk about what our denominator is factored to be. What do we have down here? This right here, the 2x plus 1, is a linear factor, right? This x minus 2 is it is quadratic, but we can look at it as what we're going to call a repeated linear factor. That's the way we'll say it. Yes, I agree. If we multiply that out, it's quadratic. But that quadratic could be factored back to this. So what we have is a linear factor, the 2x plus 1, and a repeated linear factor. So let me go back to my notes and remind you, how is it that we deal with the repeated linear factor? There it is. Repeated linear factor. So one of our linear factors is raised to a power. We have to take a letter A and divide it by that linear factor, then plus another letter, let's say B, and divide it by that linear factor squared. And we keep doing that until we get up to the power that our linear factor is. What's our linear factor for this problem, though? 2. So we're only going to have 2 pieces, right? Yes? All right. So here we go. Here comes my partial fraction work. X squared minus 5x plus 16. If you're tired, if you're falling asleep, stand up, go in the hallway, do 10 jumping jacks, come back. So what do I do with the 2x plus 1? What do I do with that linear factor? A over it, right? So that's just like the previous problems, A over it. Now with my repeated linear factor, I need to start out with the letter, so I can't use A, B, over that linear factor. Excuse me, the linear factor is x minus 2, isn't it? X minus 2, and then a second term over here with another letter C, and now let that power come up 1 to become x minus 2 squared. And if it was cubed, I would do another one, and I would have plus d over x minus 2 cubed. With me? Now, LCD on both sides. The left side's the easy part, right? That's x squared minus 5x plus 16 equals. Now, when you multiply the 2x, this a over 2x plus 1 times your denominator, right, over here, the only thing that cancels is the what? The 2x plus 1. So what's still there next to the a? X minus 2 squared, right? That's what's still there. Does everyone see that? We're multiplying this one right here. So this 2x plus 1 cancels with that 2x plus 1, and then this is what's left, right? Everything here is... See, I'm coming in on the left side and right side with 2x plus 1, x minus 2 squared, right? That's what I'm multiplying on both sides, that right there. So when that goes to here, just the 2x plus 1 cancels. So that's going to go to here, here, and here. Does that make a little more sense now? What about the b? What's still there with the b? A 2x plus 1 and an x minus 2. One of the x minus 2's canceled, but the other one's still there. Yes?
I might be confused, but like, I thought if there was like the power still on the bottom on the denominator on C, it'd be like CX plus D.
If this, what?
On top. Oh, the top.
If this was a quadratic, if what was in the parentheses was quadratic, you would put a cx plus d. But if it's linear, don't worry about the power. If what's inside the parentheses is linear, then what you put on top is a constant. If the next examples which we'll see, if what's in the parentheses is quadratic, then what you put on top is linear. Okay? Does everyone see that? Because it's well, let me finish this and then I'll talk about it. What do we have now? Plus c, what's left here? 2x plus 1. Okay, so like, again, if you're kind of like getting a little tired or bored of this, please pay attention to this. Is there a way to get a? Can we kill off b and c? How can we kill off b and c? We can make that 0 and that 0, right? So we could let x be negative 1 over 2? Negative 1/2? Okay, fine, we could do that. Can we get b? So can we kill off a and c at the same time? No. See, how are you going to leave b, preserve b, when you have to kill those two off? The only way to kill this one off is to let x be what? 2, right? The only way you can let this happen is if x is 2. But as soon as you choose x to be 2, this one's done, right? Or if you try and kill off c, you're going to kill off b. Do you see what I'm saying? You cannot preserve b while trying to still kill the a and the c. So you could try and find a and c first and then solve for b, which may work, would probably work in this problem. But this is where I want to show you the new approach, okay? This is the new approach. So watch. I'm not going to do anything on the left. On the right side, I'm going to multiply all of that out. And I'm going to go baby steps here. I'm going to do the x minus 2 squared. So this right here, x squared minus 4x plus 4, that's the x minus 2 squared, isn't it? And I've got the a sitting in front of that. Okay, next one. B, I'm going to multiply out those two. I would get 2x squared minus 4x plus x, so minus 3x minus 2. Do y'all agree with that? And then my last one, I don't really have to do anything to it. I'm just going to leave it like this. Now let's distribute the a, b, and c through. Multiply through. Mr. Sherman, your approach is good here, but there are some problems where you wouldn't be able to even do that, where you couldn't get one and the other and then get the other. There's some that you can't get any of them. So this is the way we have to do it. Okay, so I'm going to distribute this a through. I get ax squared. Watch how I write this. Minus 4ax plus 4a. So the a just went through there, didn't it? And then my next one is going to be plus 2bx squared minus 3bx minus 2b plus 2cx plus c. Do you all agree with that? Okay. Now keep in mind here, a, b, and c are just numbers, aren't they? We don't know what they are, but they're numbers. They're constants. So what I'm going to do now is on the right side of the equation, I'm going to collect like terms. So I'm going to look first at all my x squareds. X squared, that's the only two x squareds I have, right? I'm going to just put them next to each other, all right? So I have ax squared plus 2bx squared. All I'm doing is rearranging them, right? Sliding them around. Now let me collect my x's together. I have a negative 4ax, I've got a negative 3bx, I've got a 2cx, right? So those are all the things that have a single x in them. So I'm going to write those. Minus 4ax minus 3bx plus 2cx. And then finally, all the things that don't have x's. You hear me? All the things that don't have x's. So I have, what, 4a minus 2b plus c? Plus 4a minus 2b plus c. Now I'm going to write the left side of the equation. I kind of forgot to do that in the beginning. Anything here? Any questions? We're okay? Okay, now on the x squared terms, that's these two, right? I'm going to factor out an x squared. Factor an x squared out. Now watch the way I write it though, okay? Because I kind of do it a little different. When I factor out an x squared, I'm left with an a plus 2b. And the x squared, I could have put it in front, right? I could have put that x squared out in the front of the parentheses, but it's still the same to put it behind it, isn't it? Because that x squared would still distribute through and we'd still get those two terms. Do the same thing with the x's. Factor out an x. So I'm going to look at all the x terms, factor an x out, and push it to the right side. Now, watch me. Plus, in parentheses, negative 4a minus 3b plus 2c, close parentheses, x. Notice how I put a plus sign here? And then in the parentheses is where I took the negative. Negative 4a minus 3b plus 2c, and then here's the x that would distribute through, wouldn't it? Is that all right? And then all the things that don't have x's, throw them in a set of parentheses at the end. 4a minus 2b plus c. So that's this piece right here. Now let's write down the left side. Anybody see it? Anybody see how we're going to do this? Yeah, look, we're saying that this side of the equation has to equal this side, right? Both sides have to be equal. So the number that's in front of x squared here must be the same as the number in front of the x squared on the other side. And the number in front of x here has to be the same as the number in front of x on that side. And the number by itself has to be the same as the number over here. So I'm going to now, from here, create 3 equations. And I'm going to draw arrows, or I'll highlight it. This a plus 2b has to match up with the 1 sitting in front of that x, doesn't it? Do you see it? The negative 4a minus 3b plus 2c must match up with the negative 5 sitting here. And then lastly, all this junk sitting out here has to match up to be 16. Doesn't it? So let's write that down. Does this seem tedious?
So it doesn't have to equal, it just equals 1, not the x squared, right?
That's right. Yeah, that's why, remember, because we pulled the x squared out, we pulled the x out. So all of these things that we have here are the numerical coefficients. It's just the number. So let me write down the first equation. I have negative 4a minus 3b plus 2c must equal what? Oh, wait, why did I write that one down first? I'm sorry. Sorry. I meant to write a plus 2b equals what? 1. I'm going to leave a space here because I don't have a c, do I? But the next one does. Negative 4a minus 3b. I got to figure out why it does that. Minus 3b plus 2c must equal negative 5. And then finally, 4a minus 2b plus c must equal 16. This, my friends, is what we call a system of linear equations. And there are different techniques to solve that. The most widely taught is Gaussian elimination. That's where you have to try and eliminate equations, add them, scale them, does that ring a bell? There's also substitution, but substitution doesn't work as well with a system of 3 equations and 3 unknowns. But there's also another way. It's called your calculator. That's right. And you can also you could go to Wolfram Alpha to do this. I was talking to another professor about this yesterday because I was telling him I was going to be doing this. I said, what are you doing with your class for the systems of equations? He said, well, I'm going to make them do them by hand. I said, even if you get because right now we have A, B, and C, there are some problems that we may face where we have A, B, C, D, E, F. Where we might have 5 or 6 equations, 5 or 6 unknowns. And I just think it's somewhat unreasonable to have you do that mechanically by hand. I mean, should you be able to do this? Yes. Is it really worth the effort? I personally don't think so. But what I'm going to leave to you then is to figure out a way to do this. Because on a test, you're going to have to solve this system of equations. How are you going to do it? So do you have the technology in your hand? Can you utilize that on the test? So how many of you have a graphing calculator? TI something. Who doesn't? So you're going to do it by hand?
Well, I have 2 other calculators.
Okay. Do you have access to some sort of calculator? No? You don't? Okay. I might have one laying around the house. I'm not sure. Does anyone have a calculator that they want to rent? No? I'm not saying go buy a $150 calculator because of this one problem. But I would try and get my hands on something so you can use it during the test. And I'll look to see if I have one. But and you say you've got some? Yeah, it'll depend. So um, why don't we do this? How many of you have your calculator here right now? Okay. Go ahead and break it out. Let's take a little time to do this then. You don't have yours?
I don't know.
All right.
I think it's at home.
How many of you already know how to do this? You ready to?
It's a matrix, right?
Well, there's different ways to do it. There's different ways to do it.
You can solve A though, real quick.
Yeah, you can solve this. I agree. You can solve this pretty easily. If you have, I mean, you can just like figure out what A is, and yes. But if it was A, B, C, if it was A, B, C, D, E, we start to lose the ability to do it quickly. And I think it's a skill everyone going on doing, engineering problems. Everyone here should know how to use their calculator to solve a system of equations. All right, now there's different ways to do this on the calculator. I'm going to show you the way that I like because it should work for everyone's calculator, and some of them are a little different. So try and go to either the math menu or the matrix menu and find a function in your calculator called RREF. Try and find that in your calculator screen somewhere. Let me know if you find it. You found it? Okay, hang tight. Try and help other people find it too. Do you have a matrix menu? Hold on, it's at 84. Okay, go to matrix, go to math. Nope, matrix. Now go math and then go down. It's there. Did you find yours yet? Just hang tight. You got it? You get it?
I know the matrix is like right here.
Okay, matrix, go over to math, go down, it's there. And you might want to jot down how you got there, just in case. Who hasn't found it yet? Who has not found RREF? Okay, go second matrix, go over to the right, math, and go all the, oh, no, too far. Then go down, it's RREF. Y'all are good? Yes? RREF? Okay, anybody here? Well, no one here should have taken linear algebra yet, right? Who here is going to take linear algebra? Okay, if you take linear algebra, you'll actually learn what this stands for. This stands for reduced row echelon form. So what we're going to do is basically do a matrix operation. And so the way your calculator needs to interpret this is you need to put this system of equations in. So let me show you the syntax for this. The first thing you do is you'll hit enter so it'll throw RREF on your screen. So your screen should be sitting there waiting for you to input. It should say RREF, then it should have a parenthesis. Okay? That's where you should be. Now, what I'm going to do is, or what you should do, is you put a bracket. That bracket says to the calculator, here comes a matrix. Here it comes. All right? Here comes a system of equations. I'm going to begin. Then you throw another bracket. That says, and here's the first row. Okay? So first bracket means here's the matrix. This bracket means here's the first row. And now what we're going to do is we're going to put the numerical coefficients of the first row in. Numerical coefficients meaning the numbers in front of our variables. So our numbers are what? What's the number in front of A? 1. Okay. Now don't put it in yet. 1's the first one, right? The next numerical coefficient is 2. The next one is 0 because there's nothing there for C, right? And then our next numerical coefficient is 1. The way you type that into your calculator, though, so we have 1, 2, 0, 1. You go 1, 2, 0, 1. Got it? Now what do you think you tell the calculator? Close the bracket. What is that closed bracket telling your calculator? I'm done with the first row. Okay? Then here comes the second row. So I need to say Open bracket. No comma there. Okay, just open bracket now. And then what are the numerical coefficients of the next equation? -4, comma, -3. Make sure you use your negative key. Don't use your minus key. When you're putting -4 in, -3, there's a difference, right? What else? Comma, 2, comma, -5. Then what? Close it off. Start the next row. So open a bracket. I'm going to have to go to the next line here. What are the numerical coefficients of the last one? 4, -2, 1, and 16. Close it off. That closes your third row. What else do you need to do? Another bracket, because you're done, right? Close off the matrix, close off the system of equations, right? And then one more thing. A parenthesis, which closes off the function, and hit enter. And I'm going to come around and see what you get. All right. So one calculator is showing me this. 1, 0, 0, 3, 0, 1, 0, -1, 0, 0, 1, 2. How many of you see that or something like that? Anyone not see that? Who doesn't see something like that? Other than you. Did you find it? Is there a syntax problem somewhere?
Syntax, but have it exactly how it's in there. I have my bracket.
That looks right. What happened when it just said
Well,
syntax there?
Whenever I brought it up, there's
I don't know what the hell that thing is. Maybe that's where it was supposed to go, inside that box.
Well, the parentheses were over here. The parentheses were already there. I'm opening it. I'll just open it again.
Yeah. We'll work it out. We'll work it out. I'm sure we can figure it out. Yeah. Okay, everyone see this? Now, what this now represents is the numerical coefficients of the three equations after it's been solved. So what was the first variable we had? It was A, right? And then this was B, and this was C, and then equals something over here, right? So this first equation, this first line says what? 1A plus nothing equals 3. So that means A is 3, doesn't it? And this next one means nothing plus 1B equals -1, which means B is -1. And then this one means what? C is 2. So these three numbers down the side are your A, B, C. In that order, A, B, C. So A is 3, B is -1, and C is 2.
We have this on the notes,
What?
the notes that you post on our line. You gonna put all this on the notes?
This is all the video, yeah, and then there will be a PDF of this, yes.
Oh, okay.
Yeah.
I thought you were just posting PDFs.
No, the videos are there too. But the videos, you have to go to that media site place to watch them. Yeah. Question? No? This is pretty powerful. I mean, if you understand the syntax, you can do 8 equations.
This is an easier way of putting all that.
Well, it depends on your calculator.
Yeah, but if everyone has like TI, like you just go, how do you go to matrix?
I know, but some of the older ones don't do it that way. That's why I'm telling you. I'm just saying.
So that way everybody knows.
Some of the older matrix menus, the way you define a matrix is not the same as the way you define it in like the 84. So if you're using an 83, it may not work. That's the only reason I'm showing you this way.
So those are videos. Just show that being done.
What?
It shows like you writing it.
Everything. Yeah, I'm doing.
It doesn't just give you a PDF and then it's already done.
No, it's me with the audio and everything. Yeah. Okay. So let's get back to the answer, right? Shit, man, that's way up here. Now look, you still have to do a significant amount of work to get to that, don't you? You do? If you have a TI-89 or higher, if you got the one that has the brains of a TI-89, there is a function. I'm not going to tell you what it is. You can figure it out yourself. But there is a function where you could type that original expression in right here, and it will rip it apart into the partial fraction decomposition. So you could check your work. Now on the test, you're going to have to show me this, but you could check your answer that way. Okay. So what's my integral going to be? Let's get back here. My new integral is, we didn't do division, did we? There it is. So it's a over 2x plus 1. So a was 3 over, I already forgot. Someone help me. What is it? 2x minus 1
plus negative 1 over
plus negative, what?
minus
Plus 1. Okay, sorry. Then negative 1 over,
x minus 2.
okay, I know what the rest is. Thank you. 2 over x minus 2 squared dx. Wasn't that fun? Now, we're not done. We still have to find the antiderivative. The first two are kind of straightforward. 3 halves natural log 2x plus 1 minus natural log of x minus 2. Are those two okay? I had to make sure I pulled that 3 out, and then because my a here was 2, I had to come in with the 1/2, and so I just multiplied them together, 3 halves. But what about that last term on the integral? That is not a natural log. Why? Because it's squared, isn't it? So be careful with that. That's a basic U substitution. That's right. So I'm going to take this right here. Actually, I'll take it in green. I'm just going to do this quick integral. Integral 2 over x minus 2 squared dx. Make a substitution. U is equal to x minus 2. What's du then? Dx. And how could I rewrite that integral then? 2 over u squared du. That's the same as u to the negative 2, isn't it? So take the 2 out, integral u to the negative 2 du. The antiderivative of that is negative u to the negative 1. So that's power rule, isn't it? That's power rule. I'm seeing some looks of disgust. That's power rule on that. U to the n plus 1, or 1 over n plus 1, u to the n plus 1. So now I'm going to write my answer in here. So this one becomes, what, minus 2 x minus 2 to the negative 1 plus c. So I took this piece down here. That's this answer right up here, replacing my u with the x minus 2. Okay, we have 10 minutes. We have time for one more. Sorry. We see we're not going to quite get through partial fractions today. There's still a lot. Can you all believe we have next week and then spring break? We have 2 more classes after today and then spring frickin' break. I can't believe it.
Is there going to be something like really intensive on that Wednesday before spring break?
The Wednesday before?
Yeah.
No, our next exam's not till after spring break. I'm going to let all of you go and destroy all your brain cells and then come back and I'm going to give you a test. All right, let's try and go through this quick because we do only have a few minutes. Uh, polynomial divided by polynomial. We have degree of the numerator is less than the denominator, so no long division. Try and factor the denominator. Do a quick factoring over here. X squared plus 3, right? Just a GCF on that? Can you break down x squared plus 3? With imaginary numbers, but we're not dealing with imaginary numbers. So, in fact, all the calculus that you do, Cal 1, 2, and 3, right, I've already told you, there's no imaginary numbers at all. So I can't do anything more with that, right? Well, yeah. I'm going to just try and skip ahead to, I'm going to do my partial fraction decomposition thing. X squared minus x plus 6 over the factored x times x squared plus 3. Now that should turn into, let's talk about our denominator here. The x by itself is a what? It's going to turn into an a over x. So that's a linear factor, isn't it? So I have an a over x. And then I have plus, now what type of thing is this? It's a quadratic factor. And see, it doesn't break down. You can't factor it out into two linear factors. So that's as far as we're ever going to get it. So what do we do with quadratic factors? We go, yeah, do I need to go back to the note or you're okay with it? You write down the factor. And on top, instead of putting a constant, you have to put a constant times x plus a constant. So there's something kind of bigger happening here. I hope you're seeing this. Remember chain rule, right? Like, I'm going to throw this on the board real quick right here. If I have natural log of ax plus b, and I say take the derivative, right? Take the derivative. The derivative is 1 over it, right? Times the derivative of what's in there. What's the derivative of ax plus b? Just a, right? So I have a constant over a linear factor, don't I? So when I try and go backwards and integrate, I'm going to come to a natural log, right? But this is the part I want you to see. Linear on top, constant, right? The derivative of a linear function is a constant. Now, if I have a quadratic, then if I were to take natural log, let's say, of x squared plus 3, take the derivative. It would be 1 over x squared plus 3, but then the derivative of what's inside would give me what? Times 2x. So don't you have a quadratic and then up here you have a linear? That's what I'm trying to make happen. I'm saying this is quadratic, this is going to be linear. So what if we had cubic down there? What would we want up top? Quadratic. Now the book doesn't go that far, but that's the general idea. If you have a 5th degree polynomial on the bottom, then you would want a 4th degree polynomial on top. Okay. Let's try this real quick. I'm going to multiply both sides by the LCD. I get x squared minus x plus 6. Over here I get a times x squared plus 3. And then plus, oh, what the hell? What's going to happen here? I'm multiplying both sides by x times x squared plus 3, right? So when I multiply here and here, so it'll be the bx plus c, then times the only thing that didn't cancel, which was the x. Do you kind of see how at this point it's hard to sit here and try and talk about killing off a and b? Like, can you ever kill a off? You'd have to make that 0, right? It's not happening. Well, unless you have an imaginary number, right? If I plugged in, what, like I root 3, it would work. But I can't do that. I'm not allowed. So I can't kill off a. So my only other option is to expand it all out. So I'm going to multiply everything out on the right side. I get ax squared plus 3a. On the right side, plus bx squared plus cx. So I just distributed that x through. And now same game that we just played a second ago. Let's collect all of our x squareds together. And then let's collect after that all of the things that don't have, well, I have 3 different things, don't I? I've got things with x squareds in them, things with just x's, and things with nothing, with no x's. And I'll put them in descending order. So that's just me putting them in descending order. I do want to factor an x squared out on the right side because I have 2 terms with x squared. So what would I write here in parentheses? A plus b, and then x squared, and then plus cx plus 3a. And now I can play the matching game. I can take the a plus b here. That has to match up with the number in front of this, which is a what? A 1. I'll throw it in there. Then what's in front of c? What's in front of x? We've got c, right? That must match up to be -1 right there. I'll throw the 1 in there. And then we have 3a must be what? 6. Positive 6. What if they're, just so you know, if there was not an x here, but there was a cx over here, then what would c have to be? 0. Okay? So if you've got something there that doesn't appear over here, then that means there's a 0 in front of it. So it's a 0. All right, we've got a system of equations now. What's the first equation? A plus b equals 1. Second equation? C is -1. Hell, we already have C, don't we? The last one, 3a is 6, don't we? You don't even need a calculator for that. A is 2. C is -1. So once you know what A is, you can get B, right? So you can get everything here. So this one implies that A is 2. This one obviously is saying C is -1. And then this one, since I know what A is, right? 2 plus B equals 1. So that means B is -1. So you didn't need to throw this into your calculator. So the original problem becomes integral A, which is 2, over I forgot. Is it just x? What? Yeah, because we had factored out the x, right? And then plus bx -1x plus c, which is -1. I'll just put -1. Over x squared plus 3, right? dx. Damn it, we're going to go a little over. Is that all right? I won't try and go very long, but I'm just going to change that into a minus. Can you do the first one? What's the antiderivative of 2 over x? 2 ln x. On the other one, let's try a substitution on this real quick. Let's let u be equal to x squared plus 3. What's the derivative of that? 2x dx. Do you have a 2x dx up there? You have x plus 1, right? You have x plus 1? How about we do this? Why don't we take this right here and split it into 2 integrals? X over x squared plus 3. And then the other one would be what? 1 over x squared plus 3. You can handle this one with a u substitution because you're off by how much? If I take u to be x squared plus 3, du is 2x dx. I have an x up there. I'm off by 2. Y'all see I just split this into 2? Okay. And then what about this one?
Simple
Which one?
It would just be the A or whatever.
Arctan. That's arctan. That's x squared plus a squared. That's 1 over x squared plus a squared. You have a formula. So it'll be 1 over root 3 arctan of x over root 3. But you have to go look that up, that formula. I've got to stop. Okay, I'm sorry. Homework. So the problem I just did was number 22. That means you should probably start on problem like number 7 and go through 21. I think that's fair game. I'm sorry? This is out of 6.3, so I don't know the page, sorry. If anyone has the book that you can tell me.
Is it odd?
Odds. Of course, you're always welcome to do evens. Anybody have the page number? No?
334.
It's 334? So page 334. And I said 7 through 21 odd. We are due for a quiz, aren't we? I mean, like, we haven't had a quiz in a while. Why don't we make your homework a quiz grade? Let's do that. Just this homework assignment for Monday. Just this one.